Sarah, what's up? This is video number 3, live from Armenia. I helped Bryn with the current stuff, and I thought, you're still learning this new stuff while still dealing with the old stuff, so I didn't want to completely abandon the new material. Hopefully this will help you just float while you're getting up to speed with the old stuff too. So, wanted to do the DeBroglie equation. I don't know the exact pronunciation of this guy's name. I think he was Dutch. I should know, but what's more important than his country of birth, let's say, was his equation. Now, this is a very, very unique concept. This is going to be another kind of shorter video, but I want to give you some background. Around the turn of the century, I think he came up with this, and back then there was a new kind of theory in physics and in chemistry, and it dealt with the fact that, or the supposed fact, let's say, that matter, stuff, expo marker, you, me, the ceiling, whatever, could behave like matter and like light. Okay, it's called the wave-particle duality, the dual nature of matter. Basically, what it stands for is it's matter can act in wave form, travel that way like light does, and it could exhibit properties of matter like mass and velocity. Okay? How could that be? Does that mean you and I are waves? Does it mean that wave particles are actually like stuff like you and me? And he came up with an equation to relate the wave nature and the particle nature, so like energy and mass, energy related to mass. Sounds kind of like Einstein if you think about it. E equals mc squared. Energy equals mass times the speed of light squared. All like theory of relativity stuff. So it's really kind of interesting. But this DeBroglie guy, he came up with this equation. And here it is. Now before I show you, you remember from last year when you took physics, and I still can't believe you took physics before chemistry. That's impressive. But you remember this equation that it's basically this, okay, in the purple right here, which is velocity, and usually velocity could be sound, but more typically with this branch of chemistry, it's a speed of light, so we call it c, equals lambda times, I forget the Greek letter, that it looks like a v, but it's not. Basically, speed of light equals wavelength times frequency. So, meters per second equals meters per cycle of a wave. That's a full cycle. Times cycles per second, also known as hertz. So the cycles cancel out. You'll have meters per second equals meters per second. So it expands upon that a little bit. And the equation is this right here. It says lambda, or wavelength, also known as the DeBroglie wavelength, because it's his equation, okay, of anything. It doesn't have to be a source of energy or a light wave or anything like that. It could be of a piece of matter, okay? A matter's wavelength is equal to Planck's constant over an object's momentum. Remember from physics, momentum is mass times velocity. So not many people in chemistry have had physics yet, so they leave it as mass times velocity, but you can think of it as momentum. So if I substitute the value in for Planck's constant, which is 6.626 times 10 to the negative 34th joules seconds, that's what wavelength is. So the basic idea, like the conceptualness of it, we kind of went over the dual nature of matter, wave properties and mass properties. But for your math is really it. It's just plugging and chugging kind of, okay? So from your notes, I wrote these two examples down. We'll do them real quick, okay? It says, what is the wavelength of an electron moving with a speed of 5.97 times 10 to the 6 meters per second? So an electron that's zooming, okay, about 6 million meters per second. And my abbreviation, ME, mass of an electron, is really, really tiny. 9.11 times 10 to the negative 31st kilograms. By the way, you might have noticed something. This is another cool conceptual thing. Before we solve this, up here, wavelength is related to a constant, but it's also inversely related to mass and velocity. So when this is high, one of these two things, or the combination of the two, has to be low. Alternatively, when this is low, that means you have to be dividing by something huge. Okay? So before, people didn't really buy this at first, from what I've been told, because they're like, how can human beings, right? So you and I can have wavelengths? How does that even make sense? And this equation explains it, because human beings have huge masses. Like, I think I'm about 90 kilograms or 100 kilograms or something like that. If you divide a small number, this is 10 to the negative 34th, okay? If you divide 10 to the negative 34th by like 90 or 100, it gets even smaller. So my wavelength as a human being is super, super, super small. It's invisible to the naked eye, okay? But something like an electron that has a mass of 10 to the negative 31st, that is tiny, okay? So while the wavelength of an electron might still be very, very small compared to the wavelength of me, it's way bigger, okay? So small, small, small stuff has a very, very relatively large wavelength because mass lives in the denominator of this equation, okay? So really the wavelength, I mean, yes, it's inversely related also to velocity, but the most important relationship is wavelength is inversely related to mass. The bigger something is, the smaller its wavelength. The smaller something is, like the subatomic particles, protons, neutrons, electrons. The smaller something is, the way bigger the wavelength it has. Okay, so that's very important. So all you do here is you be plugging, you be chugging. Okay, so I'll write it down for you. Okay, I flip-flop the mass and the velocity. Doesn't really matter because they're both in the denominator. Mass is supposed to come before velocity. I flip-flopped them because it's 5 in the morning over here, and I'm like, don't even know what I'm doing. But we would just pop this into the calculator, and because I am recording this on my phone and my calculator is on my phone, I'm not going to do it for you, but you just pop that in. Make sure you use parentheses around this product. Maybe do this first and then do this divided by that product. And then you get a wavelength. Okay, it's called the DeBroglie wavelength, or DeBroglie wavelength. Okay, simple as that. Of course, in honors chemistry, you might have a two-step process, which means, you might be given, let's say, actually, let's do it for down here. Okay, here it says calculate the velocity of a neutron whose dB lambda, okay, DeBroglie wavelength. That's my abbreviation for it because I didn't want to write too much because it's late, honestly, and I'm lazy. But that's what it means, okay? Calculate the velocity of a neutron whose de Broglie wavelength is 505. That's supposed to be a 505. It kind of got smushed there, so I'll rewrite it. 505 picometers. Okay, pico is a prefix meaning 10 to the negative 12th. So what this would be is 505 times 10 to the negative 12th meters. Okay, and the mass of a neutron is that. It's also very small, but as you can tell, electrons 10 to the negative 31st, neutron and proton are both 10 to the negative 27th, way more massive. Okay, 10,000 times more massive, in fact, than an electron. Give you some idea. Even though they're both super, super tiny. So anyway, got to solve for it. So basically in that case, I just be plugging and chugging. I know this is going to be 505 times 10 to the negative 12th. That's going to be 6.626 times 10 to the negative 34th. And the mass is going to be 1.67 times 10 to the negative 27th. And then I just find velocity. I move stuff around algebraically. I find it. Okay? That's also a one-step process because you're just plugging and chugging into this original equation. However, your teacher may get a little bit crafty to see if you understand this stuff, know what's going on, and they might tell you something about its, I don't know. Oh, they don't give you the de Broglie wavelength, let's say. They give you, instead, okay, whose frequency is 1.7 times 10 to the 11th hertz. Let's just say I randomly made up a number, okay? If you're given hertz, which is frequency, you might notice, hey, wait a minute. If I'm given frequency and I'm looking for velocity, wait a minute. That could be a little bit pause. Okay, so we're back. I realized something. I was trying to make it into a two-step process, and this was not the appropriate time for that. But in this realm of your class, we're going to stick with that last problem. Find the velocity. It's just going to be a one-step plug and chug. Okay, but you may need to use all these different equations, or at least two of them, to help yourself out. So, for example, let's say you're trying to find the energy of a photon, and you have to use that Planck's formula, which is E equals h times frequency, let's say. Okay, but you're only given the wavelength. Let's say the wavelength of something is, and this is just me trying to say, they're not always going to be one-step processes. Sometimes they're going to be two-step processes. So let's say you have this. Okay, the wavelength of an infrared light source, and I just abbreviated the wavelength of IR light, is 686 nanometers. Now, okay, I believe that's what it is because it's got big wavelength. If it's not exactly accurate, just pretend for a moment that it is, okay? Because it's more the conceptual rather than the numbers. Find the energy, okay? And we'll find how much energy it has. Well, you might think, okay, there's no direct formula with energy and wavelength necessarily. Man, what do I do? Well, I do know this, okay? I do know that basic equation, which does not have energy in it, okay? But I do know this Planck's formula, okay? And if I'm looking for energy, I know that's a constant. That's a 6.626 number. I only need to solve for this. They give me wavelength. So guess what I got to do? I got to use this first equation in order to solve for frequency. So what I'll say is, and I'm going to abbreviate the sig figs and all that. This is just so you get it down. Okay, so you divide C by lambda, just rearranging to solve for frequency. Boom over boom gets you a number on your calculator. You pop that number back in here and you multiply it by Planck's constant, 6.626 times 10 to the negative 34th. And that gets you your energy. So sometimes you will have scenarios when it's not just a basic one-step plug and chug problem. You might have to realize that all these equations that you're learning right now, currently the 23rd of October, are related in some ways. And your teacher, being that again it's an honors chem class, they might expect you to try to, use more than one equation to get what they're asking. Okay, so there's a lot more of those that I'll go over in future videos. I'll try to do a couple tomorrow. Got this one out of the way right now. Hopefully this is helpful. I apologize for the poor example in the middle of it, but we got out of it. So hope you have a good day, good evening. We will talk soon. And let me know if you have any specific questions Otherwise, like I said, I'll just keep banging these out from what you sent me. Peace.